Welcome back, everybody. Now, this morning we have got Andy here, and he started hacking as a teenager when microprocessors were first available, and you had to build your own personal computer, which was quite a feat back then. Since the start of 2016, Andy's developed machine learning applications for robotics and drones. Today, they'll be talking about an open source distributed embedded framework that consolidates artificial intelligence, robotics, the Internet of Things, media streaming and machine learning pipelines into a single cohesive platform. Welcome, Andy.
Thank you. Well, hello everyone, it's really fantastic to see everyone, sort of, it's a bit dark, although I really wish I was sitting with you, not up here. Listening to the title, I thought, gosh, that sounds a bit arrogant and ambitious, but having a good whack at it. I think my slides are probably a little bit text dense, usual engineering fault. That URL at the bottom in yellow, that's the slide. So if you have a mobile device, jump on that tiny URL, and you might be able to see the slides close up. So I've been working on this project with several people for a long time now, and one of the aspirations was to be able to have it used commercially, because it's so hard to do open source development just in nights and weekends. And so the good news is last Friday the company I work for, Silverpond, agreed to let it be open source. So if you do like what you hear today, you'll be able to have a bit of a play. But before I start, I should welcome to the country. I begin today by acknowledging the Wurundjeri Woi Wurrung people of the Kulin Nation, the traditional custodians of the land on which we gather today. I pay my respects to their elders, past and present. I extend that respect to Aboriginal and Torres Strait Islander peoples here today. So just taking Hugh's lead, back in the day, I loved playing 8-bit microprocessors, and still do now. So this is one of my background projects. It's a 6502. But rather than an original chip, you can get these days, you can get 40 megahertz chips, throw a lot of RAM at it. Up on the top left, there's a little digital oscilloscope, so I can look at the clocks, and also using an Arduino from John that basically can load the RAM with programs, can move the clock from 0 up to a few megahertz, and also monitor the address bus. So just so much easier today, to play with this stuff compared to where it used to be. And we're on C compilers, got a little Lisp interpreter. It's a lot of fun. And this is how I guess many of us in the room started. You could really, it's very tangible. You could you wrote code and also play with the hardware. And I think these days there's many layers of abstraction that sort of keep us away from that. Mother sort of hobby is playing with Astra and dogs. Robot dogs. So this is very much a work in progress, but heading towards these things to bring this confluence of IoT devices plus robotics plus video and ML. So just play games at home and also actually hopefully do something valuable in the world. Okay, so here this morning to show off this piece of work called Aiko Services, this framework. I did cheat and use ChatGPT just to pick a 3-word title for this slide, and that was it. But anyway, got to keep up with the cool kids. I work at Silverpond, which is a fantastic place. The business team and the engineers are great. We basically make machine learning products, and I'm a systems engineer, and I basically do the infrastructure support and those sort of things. As often as I can, hang out with friends at the hackerspace and basically play with devices and robots there in my spare time. So today, we'll discuss this embedded framework, try and give you some context. I was thinking at first I'll just big lead up and the big demonstration at the end. And I thought, no, that'd be the worst. Why don't I just give you the demonstration at the start, and if you like it, you can stay. And crash and burn early. Try and cover what this framework might be good for, how it differs. Try and give some technical details, but not try to bore you to death. Although I couldn't tell if you're sleeping or not. And then I'll also just cover some of the aspects of trying to get synergy or the best outcome of working both commercially and as a community developer. And then maybe discuss a little bit about what next. Okay, so it goes without saying, it's been an extraordinary time over the last 60 years, 30 years, 10 years. With all the software we could possibly want, just there at a touch of a button. And for those fortunate enough, we just we're connected all the time. We have our devices in our home, in our pockets, and so on. The hardware we have now is amazing. Just looking at the numbers. The transistor count, so looking back to that first slide, that microprocessors in those days like 6502, about 3,500 transistors, a clock rate of megahertz, and one core. These days, the transistor count is about 6 orders of magnitude greater, the clock 3 orders of magnitude greater, and the cores maybe about 1,000 times fold. So it comes to about 10 to the 12 increase in I guess raw horsepower. It's pretty crazy. But that's what's been enabling AI with its insatiable need for data and compute. And it goes without saying that last year was pretty amazing in the way that just from a website, pretty much anyone who's connected can play with these tools now and achieve extraordinary results. And just yesterday, OpenAI did a bit of a preview on GPT-4, which won't be out for a few months, it sounds like. But yeah, there's a link there for anyone who's interested. It's just a short demo by this co-founder, and basically they've just lifted the game on most of what it does. Okay, so you hear that if you sort of can describe the problem, you're halfway to a solution. Sometimes it feels like that, but other times you just go, no, it still seems like a ton of work to do. But anyone who's works in any of these domains of Internet of Things, you might work with media, you're in the ML space or robotics. Each of these things are pretty much more than a career's worth, and they all have different frameworks and tooling, and it's can be quite difficult, and you want to pull your hair out when you try and integrate these technologies. And so the hardware is different. Your concerns when you're doing media are different from when you're doing machine learning, and yet if you want to build these sort of modern applications, you need to bring all these things together coherently. And on top of that, there's also just all the other concerns you have in terms of failure and security. How do you configure? How do you persist? If you've got multiple programming languages, so it's pretty challenging to build systems these days where they're reasonably reliable, robust, secure, and so on. Let's check on. Cool. All right, so I'm just going to start off with the demo. I was very kindly allowed to use this, even though business people are very, very concerned about how an engineer presents stuff, because we don't mind things being a bit ratty and daggy. And this is really just here to show off the open source framework. So as I said, I work for a local machine learning company. And we've done the classic pivot from consulting over the years to try and productize what we do, and that's can be quite challenging. And the actual product itself is much more than the piece of work I'm showing you today. But this is probably the best demonstration of what it can do in terms of using WebRTC for video, capturing data from a device, either a camera or in this case a little IKEA train, that's what I have to show. And there's also, when you're doing commercial work, you're confronted with problems that you may not get when you're just doing your hobbyist work, because when I know when I'm doing my own projects, I particularly try and do the things I think I'll be able to get away with. Basically tailor my efforts to something I think will be doable. Whereas often clients will give you such a situation which you go, oh man, that's so hard. Can we do something a little bit easier? But it is a good opportunity to really make sure your work is battle tested. And I believe very strongly that there's good synergies between commercial and community. That we just have to look around you today to know how the quality of people that are out there in our community and around the world. And also, but you also know we're always struggling for funds and opportunity of people finding work and so on. So I think they bring these two different, organisations, either the community or commercial, is really important. So what I found is I've been working on this for a very, very long time. Just conceptually, it's been used on nearly 4 projects now through my career, just as I've gone from job to job, and it's gradually got better. But one thing that sort of happened during lockdown was, we normally try and achieve work-life balance, be social and family and stay healthy and so on. And just in Melbourne for at least about a year and a half, it's like, nope. It's a very unfortunate situation, but I was thinking to myself, well, if I can't get this project done now, when I'm not allowed to leave the house, and that's the stuff, I'll never get it done. So I thought, no, this might take 6 months to a year, and here we are 3.5 years later, and still a lot to do. But it's true. If it wasn't for being locked away in my own home for many months, it would never have happened. Okay, so and then just to give some context. This little bit of framework basically forms sort of the infrastructure for a bigger product at work, at least in terms of some of the back end and some of the distributed computing aspects. It's been often when you're working in an organisation, you have to do that thing today. You don't have 2 weeks to get it right. You have to basically do something for a client that you have to do immediately without giving it all the thought it needs. Whereas sometimes with open source working, you can take the time overnight or weekend to think through that design or basically improve some of that tech that it really sucks, but won't have the priority to do on Monday. Okay, if you go. So this is a bit of a conceptual view of the overall product. Basically, the idea is to take data from the field. It could be devices and things like basically maybe cameras in the city, like looking after the road system, or it could be in rural, basically looking after cows that look surprisingly like cockroaches, I think. But basically, where's your livestock, or basically resource management, or the oceans. So one project we've worked on is basically fish counting to make sure that the state of the fish stock and helping out marine biologists. So that comes in as a series of rich data and streams. It could be GPS location, it could be LIDAR, it could be video, it could be hyperspectral, and then you basically want to send that through data center pipelines. And one of the advantages of doing things as a data center is that you get the information from all of your devices in the field. So basically you get this more omniscient sort of overview and make decisions that you can't make as an individual device on the edge. And then that goes through, we basically integrate to other people's enterprise systems, which they can make sense of the data themselves, and also basically use ontology or taxonomy to break down the relationships between the things you're seeing in the world. So that's sort of what it's aiming to do. Okay, so what I'm about to show you is this is a bit more of a complex view. The blue bits are basically about WebRTC. WebRTC is pretty amazing. It basically allows you to have bidirectional audio, video, and data that gets through firewalls, and everyone's using it as a result of COVID on all their Zoom meetings. So there's a part of this where you have to set up the WebRTC connection. All the white bits, they're all services that are where we sit on this framework, are sending messages to each other, and the green bits is just the underlying mosquito. So what we end up with is a web browser is going to over WebSockets talk to the back end, to the registrar, find out what sort of services they are. They're particularly interested in the data sources like the camera from the train, an RTSP camera in our office, which I should have checked before presenting today, and also like a WebRTC camera on my laptop. It's a selected data source which allows the web browser to go to the signaling server to set up the WebRTC connection. Once that's good, the web server can then the web browser can then talk to the back-end WebRTC manager to then set up a session client, and then once that's all good, the data streams through and ends up going to the ML model, then back to your laptop. What else is worth mentioning? And also, interestingly enough, the web browser work is all in Go. On top of WASM, which is very, very cool. So basically run the same code in the browser as the back end. Okay, well, let's see if I can bring this together. So I'll just refresh this. So this is the web browser view. What you'll notice is up in the top left is a number of services, the mock train, the live office camera and face detection. In the middle is the chart. So having found the services, let's just have a quick look at one. But using eventual consistency effectively over MQT, all the data about that train is coming back to here, like its location, its speed. And also, it also provides UI hints. It says, look, put my GPS coordinates on a map, put my speed on a chart. So just off the screen here, there's some chart information for all those devices. And just to show you on the back end, you can see that's the actual devices. So we've got a little dashboard, which I'll talk more about later. And if we look at that train, we can actually see the same GPS coordinates here in that middle view. So, one of the goals of the system is to make complex systems be able to inspect any part of them and see what's going on. So let's just see if this works. Right. Hang on. I've gone. That's my presentation. Here's the real thing. Okay. So this is basically taking a pre-recorded video file because the train is here today. See if this comes up. What I can do is I can check the back end and see why it's. Nope, I have to do a refresh. Oh, here we go. Yay, team. So that's video that's being sent through the back end to the front end with WebRTC. Under normal circumstances, it'd be going through the ML model, and if it detects signs or buildings or trees, that lets you know. So that's sort of the first thing. Now, the second thing I'll do is I go up to here, and I can send a command through to the train from the web browser, just saying stop, and so we can see the video stopped, and so it's one of the trains. And if we look at the back end, we can see the train's also stopped, and its actual state has gone from running to false. There we go. And if I wanted to, I could just from this dashboard, I can go and say make that true, and hopefully. Yep, train's going again, fantastic, and it's off. But the video isn't. Oh, hang on, I know why. I've got to. Damn. User interface bug. That should start the video up again. The second thing I can do now, I just have to do a refresh, is just see if I can show the camera's live stream. Okay, so it's going to be the office camera. So this is in a building that's actually looking over the river just up the street from us, and so you could almost but not quite see where we are. There's that bridge on the far right is just across the river from us. So that's an RTSP camera in office, and what I'm hoping to do with the ML engineers is train a model that recognises boats and trains and things like that. Just count traffic basically to demonstrate. I was actually running this last night just in case I had a failure today, and every hour across the casino they've got these little gas towers, and they send up little gas balls because global warming. It's been doing that for decades. Lots of fried pigeon, I believe, I don't know. I might take a few seconds and maybe a bit later to show you the view, because they've got these massive gas balls over the river, which is pretty impressive in black and white. Okay, the last thing I'll show you while we're on a roll is so look, in some ways this is not that exciting because we see video and stuff going to browsers all day, every day these days. But it's really more the architecture that was put in place to hopefully make this a little bit more modular and easier, I guess is the point. Oh, hang on. Sorry, I went and showed the same thing again. Sorry. Nice, fast internet, fantastic. Thanks, Steve. He's all the volunteers are awesome as always. Now this takes a little bit longer because the ML model takes about 10 seconds to load up, maybe a bit longer, and that has a little problem because I have distributed leases, and the lease time was also about 10 seconds. Saying if we don't hear back, assume there's a problem, but I have actually extended the lease out, so that should be up now. There we go. No, hang on. Oh, sorry, I keep going back to my demo page. Oh, here we go. That's actually working reasonably well. Yeah, so this is just round trip from the camera. Everyone can see it okay? Yeah. And the nice thing about WebRTC, we should be able to get roughly less than a second latency. So from this camera up to the data center and then back down again. So wow, the demo worked. We can all go home. All right. Okay. So hang on. That's actually going to. That's the one I want. All right. Might just speed this up a bit. So there's been lots of influences. So one is the actor model. It's a model for doing concurrent computation with distributed systems. Everything is an actor. It was created back in '74, and Guy Steele was curious about whether it could actually be not just theory but work, and he invented scheme specifically, and that for other reasons as well, to test out the actor model, and along the way invented call by continuations. And I think he's probably like 21 or something like that. It's a bit scary. But also Erlang is probably the most famous use of the actor model. The Erlang language powers, or did power, a lot of the world's telecommunication networks very, very reliably. And also Erlang's used in WhatsApp and WeChat. Who knew? So the actor models, maybe not everyone's heard about it, it's pretty successful. Another influence for me was Genie, which was a distributed system that a little breakaway group in Sun Microsystems did, which super well designed by some very, very smart people, very experienced, fully asynchronous, services-based, just use Java interfaces, so you didn't have to worry about any stubs or marshalling. But wow, the out-of-the-box experience was just really, really tough. It was very challenging to use, so unfortunately it's defunct now, but it was a great thing to learn from. But just briefly on actors. Actors can do three things. They can basically send messages to other actors, they can create other actors, and they can also change their state, which means that their behaviour on the next message will change. And the great thing about actors compared to other, just having a whole myriad of services, is it's just easier to reason about your network. It just simplifies things, but without compromising being able to get stuff done. So some more influences. Everyone knows I love Lisp. And in this system, we basically use Lisp for the messages. I think of everything as being a function call, which can just translate directly to a Lisp S expression. And what's great is that allows you to do mobile code. That S expression could be a data structure, but also could be a filter. So you basically say to another node in a network or another actor in a network, here's this filter I want you to apply. So it can very easily move your computation around the network. Of course, keeping security concerns in mind. But the great thing about the Lisp machines back in the day was everything was in Lisp. They had hardware instructions, the operating system, GUI, applications. It was just turtles all the way down. It just showed you what could be done. The other inspiration is Smalltalk, which is Alan Kay said, look, you always intended that it really should be message-oriented, not object-oriented. But the amazing thing about Smalltalk is even the language itself is where you basically send messages to other parts. So your if statement is performed through sending messages to the true block or the false block. It's and if you've seen Smalltalk, or if you haven't seen Smalltalk, you can download Squeak, and it runs on modern operating systems, and you can basically see what an amazing system this was, where you can click on a window and it'll take you to the source code browser, and you can change the behaviour in the system on the fly without rebooting. In fact, the story goes, which is true because you see Steve Jobs talking about this on YouTube, when the Smalltalk team invited a number of companies in to see what they'd done, because no one had really ever seen a graphics user interface before with Windows and mice, except a few researchers and Doug Engelbart, of course. And they showed him about 6 things. And he said, look, I was so blown away by what the first thing I saw, which was the Windows, which he obviously took back to Apple. He totally forgot about what those other things were. Ethernet, laser printing. But the thing that captured his imagination was, according to the Xerox researcher, was how they did select was really ugly. It basically just blocked out the whole text, and it was ugly. And Steve asked him, well, that's just terrible. What can you do about it? And the engineer said, look, hang on, give me a sec. Found the Smalltalk method. Said, look, if we subtract this rectangle from this rectangle, basically this nice outline. Did that in about a minute. Didn't stop the system, and then he basically had almost like a moving arch select type thing. I think that's why Mr. Jobs forgot about all the other things. Anyway, moving on, because that's right. So, some overall design principles. Complete systems done through messages. I want these things to be very lightweight so they can run on embedded systems. And I really want to think about it in terms of things as function calls. So basically say, I'm just calling functions between my actors locally or remotely, and not have to worry about marshalling or unmarshalling, all those things. And there's something about just simple human readable messages that are so easy to debug, especially if you're using MQT. You can basically just do a mosquito pub to basically do some injection testing to go, hey, let's just exercise that actor or device or whatever, and you can just also subscribe and see what's going on in your system. So it's really great, but of course that does collapse a bit when you've got lots and lots of things going on. So in the system, pretty much try and use Lisp and MQT everywhere, but the applications, if you want to, there's often good reasons or pressure to basically use JSON and Avro for validation or protobufs or whatever. That's fine too. The thing about when you have a fully asynchronous system is you can't really do blocking calls. Do RPC, where you make a call, a request, and expect back a response. So the simple rule is functions don't return values, which makes it much easier to do a distributed system, but also makes it a little bit more difficult to program in terms of, do you do callbacks? What if you're going to create something and you want to get its reference back? That becomes really hard. But there are ways around that. For example, using eventual consistent cases, you can basically say, I'm interested in this state over the network, like this reference or its computation result, and that just lands in your cache, and when it's seeing something, just do a local, hey, get that value. So the problem is if you're only doing, if you've fundamentally got a request-response system based around HTTP or REST or the GraphQL, all these things, is you just go, we'll just use asynchronous just for these things where we need speed, and it becomes this special hard case. If you tackle it early on and say, no, we'll just try and make it easy from the start, a lot of those problems go away. The other thing we use is dynamic proxy objects, so we can have layers of abstraction, so we can abstract out different third-party things. So we can have MQT as a transport, or ROS, or high GraphQL going over HTTP. So, or we can swap in different security models and so on by doing that. And just as an aside, there's a great talk by Kevin Greer around the foam group at Google, and he just is comparing the advantages that Unix had over Multics because they did what was called coding the perimeter. They basically looked at their cross-cutting concerns, when you basically say, well, we've got functionality on one axis and we've got, I guess, the things you must do, like persistence and configuration or communications on the other axis. And instead of basically trying to, for each individual program, figure those things out over and over again in Unix, because we construct things with pipes and so on, and small composable pieces, presumably Dennis Ritchie and Ken Thompson were able to move much faster because they were coding along the perimeter. They weren't trying to fill in the whole area. All right. So just how that looks very quickly is I've got a couple of actors here. So actor 0 wants to create actor 1, so it's going to talk to a lifecycle manager to do that. So the blue message is around creating the actor. So actor 0 says, look, create an actor to the lifecycle manager. The lifecycle manager will create that. That actor, actor 1, that reference gets back to actor 0, and then the actor 0 can then say, okay, pause, run, delete, whatever you want. And so the main thing I want to show here is that within the actors, you're just using function calls. Using the dynamic proxy, we can just turn those into VS expressions, send those across the network, unmask them for you. And so you don't have to worry about all the machinery. And the other thing is the green bit, that's the cache. That's the caching. We're basically using eventual consistency. So just one effectively class or instantiation for a producer, just wrap your state, and the same thing on the other side. We just have a consumer that says, look, this is the state I want. You can filter that state so you don't get all of the state, just the bit you need. And then what you can just do is just dip into your local cache and get the most recent value. So hopefully that gives a bit of a conceptual view. All right, so some distributed design principles. Back in the 90s at Sun Microsystems, there was this list of things that are basically fallacies. If you believe that the network is reliable, your application is not going to be reliable. And they had a list of 7 of these, and then James Gosling added the 8th. Even though Java did make the network look a bit homogeneous back in the 90s for a while, it's not true. All the devices we have these days are quite different. So these are things that if you make any of these assumptions in your architecture design, you're going to come hit some potholes for sure. And I'm not trying to basically try and cover all of distributed systems theory in a few minutes, but I sort of mention a few other things. So there's CAP theorem, which basically says 3 things, you can only have 2, which is partition tolerance is like, can you handle network failure? Consistency, do you want when you do writes and reads, does everything have the same value? And availability, can you see that piece of information from another part of the system? Things like databases, which do ACID, they really work hard to make sure that no matter what, you have availability and consistency. But the problem with that is you've got to deal with network failure, always. So that was about 20-odd years ago, it was the CAP theorem. In the last dozen or so years, there's what's called PAC ELC, which says not only do you have to worry about CAP, which is basically choose to have partition tolerance and then worry about available consistency, even if the network was good, you still have to choose between whether you want to have good latency or you want everything to be consistent, because there's a bit of a trade-off there. So in Aiko Services, what we've done is they said, look, you have to worry about network partition and what to do when the network fails. But then after that, basically using a form of or slightly stronger form of eventual consistency, which is effectively called sequential consistency, where you still preserve the right order, and basically the data will be available eventually. The other thing we use is something called distributed leases. So if you basically done some operation that basically causes another part of the system to acquire some resources. Maybe you've made a database connection, you've now got a connection there. How long should the server hold onto that? And if you haven't agreed up front and the network fails, you've got no way of carrying on the conversation, like closing out properly. So the thing about leases, you can say, look, I'm going to lease for 5 minutes, and if you don't hear from me, both sides can assume it's done and over. So even in a network partition, the two parties will know what the situation is. 5 minutes went past, you haven't heard from each other, it's all over. Very powerful, very simple but very powerful technique. Okay, so people who've come along to the OHMC know that we've used this thing called the Aiko engine, which is a bit of MicroPython code for the, like the swag badge and other things. So what's the difference between services and the engine? Basically, the engine was really about providing a little bit of an event-based model, some little peripheral drivers for buttons and screens and networking and so on, just purely about the device. But the services is this framework I'm discussing today, so that's sort of the difference. And so the services basically says, here's the definition of all the protocols, provides a reference implementation, and then the engine can do everything you need on the device or wherever, and then says, oh, and here's how we can use services to interconnect. They're the URLs up now. Okay, just check how I'm going for time. 14. Yeah, not the, a little bit behind. Okay, so this is how Aiko Services look from a very high level. The main service is the registrar. So the registrar allows you to join and discover all the other services. So in this case, we just have two services on the bottom, 1 and 2. They both add themselves to the registrar with an S expression, which is basically just add and a bit of detail, a few details. So and then it allows to find each other by querying the registrar, of course. And then service 1 can find service 2 and do output. So it's nothing too revolutionary there. Right. So what is a service? Well, pretty much like every other service, every other definition of service. So a service can join the network, it can be discovered by other components, it can then receive messages through subscription, it can publish messages. But what we've done in Aiko is also define some additional things that services have. Most importantly is topic prefix. So in MQT and other messaging systems, you always choose topics, and often you do that by saying, oh, well, what's a temperature sense? So say it's the topic will be kitchen/temperature. In this case, Aiko auto-generates your topic, which is based on your namespace, so it can basically partition things for reasons of security or testing or whatever, so you have these different namespaces, the host that you're on, the process ID, and the service ID. So those things give you a unique topic path, which is also useful because I say, oh, what host is my service running on, or what process if you want to kill it. So it's kind of a bit useful that way. But it also means there's no collisions. And what the service or device can do is it can then just append additional strings saying, oh, I want an input topic or an output topic or logging or whatever. We also can name the services. The protocol defines what interfaces the service implements. So it could be, okay, it's always going to be a service, possibly an actor. It could also be a temperature sensor, or it could be something, it's a category or group of other things. So the interface is to say all those things that you are, which is also another way of finding something. So you basically could say, oh, find all the persistent stores, or databases. We also have the transport, which means we can swap in other transports, like ROS, not just MQT. And the tags are really how you can find things. Like with email, you can basically tag services and say, create new keywords and give them values. So right now, using that for eventual consistency, you can say EC equals true, 10 minutes, cool, better speed this up. To basically say you support eventual consistency, UI for UI hints, and so on. Okay, so the registrar is we support primary and secondary registrars. that's just the messages that you can send to a registrar. So add, remove, hypervalue others. Share allows you to say, look, I want to have a filter. That's all the stars are wildcards for the various service fields. Here's the service fields I want you to filter on, and those messages will come back into your cache, so you can then check that. The other thing you can do, which is used by the dashboard, is also get the history. So the registrar keeps a history of services that have gone away. So you might have a service that starts up, dies, and goes away. You want to be able to at least know that it ran, and also be able to look at its logs. Okay, so I'll quickly show you the dashboard. It's a bit like, so you saw it briefly before, it's a bit like top, interacts with the registrar, shows you all your services, it allows you to interrogate and check all the variables and logging and so on. So let's see if I can just quickly show that again. Let's do this on the back end. Actually, I'll do it here. I'll do it on, hang a sec. Right, cool. This is just running on my home server. So we've got the register up there. We've got two swag badges. So that's ESP32s. But I could just locally, I can just add another service if I hang a sec. Sorry. No good type here. So search examples. Hello. So this is the equivalent of hello world. Hopefully that's going to work for me. It's fun of doing things. Oh, actually, I know what's happened there. Wrong screen. That's up on our back-end server. Whoops. Let me just do it on the local machine now. Yeah, so it's like SSH but worse. Hang on. Okay, so there's hello, but much faster. Yay, team. And so we can see the various variables, like its life cycle state, it's ready. We can change the log level. We can change that log level to debug, for example. So it's now you can now change to debug. We can look at dictionaries and so on. Another one I like to do is have the version number and the source code for the service. So the idea will be actually just click on that, it'll take you the source code for that service. And you also see the tags. So this service supports eventual consistency. And what you'll be able to do is go to log and be able to see the logs as well, which I probably haven't got time to show that. But the idea is to have a dashboard that allows you to pretty much inspect everything. All right, I've got 24. So, right, so speed up a bit. So MQT is great. It's widely supported. It's very lightweight, but we can swap out for other transports. Services versus actors, so I sort of swap back and forth between the two, but services pretty much allow you to do anything you like. They can be multi-thread, there's no constraints, whereas actors, because of the actor model, have got constraints that make them easier to reason with. They have an inbox for incoming messages, which they work through one at a time, and that prevents race conditions and so on. So you can have, because I want to have this to be very lightweight and scalable, we can have one service per process, which can be quite heavyweight, or you can have multiple services per process. So just to show you that very quickly, I'll just go back to the Hello World example. If I say, make 20 of these, there we go, we've now got 20 Hello Worlds, all in the same services in the same process. So my aim is to basically be able to scale up to 1 million services on a single machine. The other thing I might be able to quickly show is if we go to Lifecycle Manager and say 10, that's just using the Lifecycle Manager to create 10 clients, and you can see that they're on different processes because their process ID is different. So yeah, so we support those sort of things. And these features are little components you can compose into your service, so we don't have to write these caches and these creating other actors all the time. It's already been done. So finally, we've got pipelines. Pipelines allow us to create data flow checks, and this is what we use for the machine learning and also for GStream media pipelines. And the pipelines are just actors, so you just link them together through the topics. And also the pipelines themselves are pipeline elements, and so you can have a hierarchy of pipelines that consist of other pipelines and so on. So it ends up looking a little bit like this, where up the top left you've got a process manager which can use those green lines to create all the actors, and then they all then discover them. They all go and join the registrar, and the pipeline manager can then hook them all together. About 2 minutes. Yep, thanks. 4. Thanks very much. Okay, so hopefully this has given you a bit of insight to how this framework can bring all these different domains into the make them consistent to use as an application developer. So devices are services, pipelines are basically a data flow of services, same for the ML models, and other frameworks like ROS, and we've already done this for the Play framework, can just be abstractions, transport abstractions, so we hired that away. So I was going to talk a little about why buy versus build. It's often comes up as engineers, we want to build new stuff, but you want to make sure that what you're doing is there isn't already an answer out there already, that the existing solutions are definitely not good enough, and also internally have good support from your business engineering team, and you're able to support stuff long term, for supporting the community and so on, and you're actually delivering an advantage. Hopefully we'll try to accomplish that internally here. The other is open source. That's quite a challenge to convince the business people to allow you to do this. There are benefits, but also concerns around giving away competitive advantage and losing control of the terminology and so on. But really, I believe it's a virtuous circle that as you put things that businesses pretty much have entirely depending upon open source, and if they don't contribute back, that's just obviously not a good thing. So here's a quick list of what comes up next. So incorporating ROS, actually documentation examples. There's a few people like Thomas figured all out himself without documentation, but go Thomas. Yeah, I was just one night, okay, hang on, there's a device. I don't recognise that device on my network. There's Thomas's swag badge over in Adelaide. And just quickly, been chatting to John about whether we should finally tackle our Open Hardware Conference. So if anyone thinks this is not a totally insane idea, please come and chat to us. I'm going to be heading over to the Open Hardware Summit and see how they do it on the other side of the planet. Anyway, but we'll also be bringing in other languages and also incorporate bringing in some of our previous OHNC projects. Support your local hackerspace. They're great places, and we lost a few during COVID, but the ones that have survived are fantastic. So there's probably one near you, or you should perhaps start one. And just like to thank everyone, the people in the community, John and Rowan at work, Linux Australia, and all your volunteers. I think give you guys a round of applause because you brought us all back together in. And also everyone here, and of course John. Yeah, that's kind of it. Rushed through it at the end, but I got there. Amazing. So it's back in Brisbane. Hope you have John doing his Jedi mind tricks. I think it was about only a couple of months before the Microsoft Kinect had come out, and also the Parrot drone, one of the very early consumer drones. And I think John and I were just chatting one day and said, well, what can we do for Brisbane? And it's like, hey, we'll smack these two new things together. Which was actually part of John's broader vision for stuff. Another one was this is us doing presentation preparation the night before in the hotel room. Also another chat. Typical LA volunteers. The whole of Brisbane gets trashed by floods, and in 11 days they completely redo a conference. I think this was to prank Lana Brindley, maybe. All right, we don't.
Destroyed that inflatable unicorn not long.
And she's here in the room.
But it was very tasty. All right.
Unfortunately, we don't have time for questions. I'm sure you'll be able to catch Andy around and about. I just want to say thank you very much on behalf of the team here for coming and talk to us.
Thanks very much. Thank you.